All right, hello everybody, and welcome to the homework helper for Statistics 2, Stats 2. Let's do this. So the first thing that it's talking about is the law of large numbers, and the law of large numbers pretty much states that as a sample size goes up, its mean gets closer to the average. Okay, so as the sample size goes up, its mean gets closer to the average. So when you think about, let's look at number one. It's talking about the idea of rolling a die. Okay, and it says if you're rolling a die over and over again, and after 6 rolls, almost got it. Your friend rolls 4 5s. Are you surprised by this? And it's worth thinking about. I mean, 6 rolls, even in that little experiment I just did, I think I rolled 2 of them. To roll 4 is hard. But why would rolling 4 out of 6 being 5s, why would that be surprising? Well, it's because each number, by definition, has a 1 in 6 chance of happening. So of rolling 4 5s, that's 1 in 6 times 1 in 6 times 1 in 6 times 1 in 6 times 1 in 6. These are all the possibilities of it happening. And what we would expect if everything were perfect, if you were roll a dice 6 times, is you would roll a 1, you'd roll a 2, you'd roll a 3, you'd roll a 4, you'd roll a 5, you'd roll a 6. But we know that's not actually how it happens, because in fact each one has a 1 in 6 chance of occurring. So it's not completely unlikely that a number will come up twice in a row, right? Because the dice doesn't remember. The dice doesn't say, oh, I rolled a 5, I can't roll a 5 again. Oh, I rolled a 2, I can't roll a 2 again. Oh, I rolled a 1, I can't roll a 1 again. Oh, back to a 2. So the die doesn't remember. The chance is still the same. So I think if you're thinking about 4 5s, right? When there's 6 possible options, one option comes up 4 times. Yeah, that's pretty significant, right? That's going to be 1 times 6 times 6 times 6. That's a infinitesimal number. So yeah, that's unlikely. That's very unlikely to occur, but it's not unheard of, right? It's not out of the realm of possibility, even though it's unlikely. But now let's scale this up for a second. So after rolling a die 50 times, you notice that you rolled a total of 25s. Now is this surprising? Is this more surprising, right? Well, if we expected, 1 and we got 4, that's 4 times what we expected. How many 5s are we expecting to roll out of a 50 rolls? So that would be what? 50 divided by 6. So let's do it the hard way. 60, 50. What is that? 6, 12, 18, 24. So 48 would be 8. So that'd be 8. That'd be 48 and 2. 20. So like 8.3 bar. So we would expect to roll 8 5s, and instead we rolled 25s. So is this surprising? Yeah, this is even more surprising, right? Like this was a small sample size, right? Small sample size, right? Rolling 4 5s in a row, that seems really, really unlikely, but it's a small sample size that can happen. Even in my test, you saw I did 2 out of my 6. Like it's crazy. But when we're thinking about a lot of dice, if we're thinking about rolling it 50 times, like that's a huge factor more. That's so many more. So even though we're expecting 8.3, because we've rolled it so many times that we've got over double, that's actually more astounding, right? That would make us think that there might be something wrong with the die might be weighted. So even though the factor isn't the same, right? Even though this is twice and this is 4 times, and 4 times is clearly larger than double, because we've rolled 20, or I'm sorry, because we rolled 50, because we rolled 50 die, it's kind of amazing that we would get 25s out of that. That's a huge percent. We are again expecting a sixth, but instead we got 2/5 of the rolls. So that's a lot. Okay. Third one you can do on your own. Let's go to the next section. applying the properties of normal distribution. Okay, so if we look at the population of NBA players in a and we're assuming it's a normal distribution with a mean of 6 feet 7 inches and a standard deviation of 3.9 inches, Greg is considered unusually tall for his high school at 6 feet 3 inches. So what percentage of NBA players are taller than Greg? So I find it's really helpful to think about our standard deviations. Right, if we have, so here's our mu. Here, I'm actually going to do a table, right? I'm going to do a table. We're going to have our mu. We're going to have some plus sigmas, whoops, plus 2 sigmas, like so. And we're going to think about this, okay? So if we're going to say that the mean is 6 feet 7 inches, you know, my brain works the way it does. So we'll leave that for now, but part of me wants to just convert that completely into inches, but we'll leave that for now. And we got a standard deviation of 3.9 inches. So that means if we're adding 3.9 here, this is going to be 6, 10.9, okay? And then if we add 3 more, that's going to be 7, 3.9, so that's essentially 11, 2.8, yeah. And then likewise, if we go backwards, we're essentially subtracting 3, so that's 6 feet, 4.1, and then 6 foot, 1.2, and then we can figure out minus 3. Okay, so this is where we're at. Okay, and then Greg is considered unusually tall for his high school at 6'3". So he's just under 1 standard deviation away. Oh, 3.9 inches, not 2.9 inches. So this is 3.1. Yeah, 3.1, and this would be 0.2. My bad. So here's where Greg is. Greg's straddling this line here. Here's where Greg is. Greg is sitting at oh my gosh, I didn't do this on the screen. Oh boy, of course I didn't. Okay, so essentially what I did is I created a chart. Here's our mu, 6 foot 7, plus 1 standard deviation, plus 2 standard deviations, plus 2 standard deviations. Here's our mu, minus 1 standard deviation, minus 2 standard deviations. Okay. And so this right here, 1 standard deviation down, is where Greg is. Let's think about this as a normally distributed graph. Okay. So once again, here's our mu, 6, 7. Here's minus sigma, which puts us at 6 foot 3.1 inches. Okay, and this is where Greg is. Greg is right here. Greg. Okay, there's Greg. So now what we're being asked is what percentage of NBA players are taller than Greg? So what percentage are taller? Well, we have all of this to calculate. We have this part, this part, this part, this part, and this part, and only this part is underneath them. So to be able to figure that out, we need to know what our distribution curve looks like. Luckily, I gave that to you. So we have that on the inside front cover. If I don't have it on the inside front cover, I've given it to you before. So here's our graph, right? Here's how it's supposed to look like. So we know that 34.1 plus 34.1 plus 13.6 plus 2.3. All of that's the population that is taller than Greg. So it's 34.1 plus 34.1, 13.6, 2.3. So that's 1, 2, 3, 9, 10, 1, carry the 1, 4, 5, 9, 12, 14, carry the 1, 4, 7, 8. So 84.1% are going to be taller. 84.1% are taller. Okay? And again, we're just using this chart to be able to calculate that. I think the next question is how much is smaller? So if these are the ones that are taller, right? Because this is where Greg lives, then this is the percentage that are shorter. So that's going to be what, 15.9%. Okay? And sure enough, 15.9 and 84.1 add up to 100%. So we can see where everybody is on this. All right. So essentially, that's what these questions are going to be asking us to do. They're going to be asking us to use the mean, use the mu, use the standard deviation, use the sigma, and be able to build these charts so that we can answer these questions. Okay? How tall would he have to be in the top 2.5%? You can figure that out. And I believe the other questions are very similar, right? Yeah, we're just changing the average. The average height, so here's our mu, standard deviation is our sigma. Jordan's drinking up a coffee. The average time, 10 minutes, that's our mu. Standard deviation, that's our sigma. And so we're just constantly going to be rebuilding these charts based on this information. Okay? With all that, I think you will be able to accomplish all this, and I will see you next time.